Hello, this is the second part of the 7th lecture of ECE 141 about optimal detection of memoryless digital modulation. In the previous part of the lecture, we talked about maximum a posteriori decision rule and the maximum likelihood decision rule. And in this lecture, we will assess the performance of our different digital modulation schemes or different memoryless digital modulation schemes using a simple parameter that we call the bit error rate or the BER. So we'll analyze the performance of our different memoryless digital modulation. So some examples like your MQAM, your ASK, and your FSK. We'll talk about how they perform in this part of the lecture. So if we're talking about bit error rate, we're talking about the noise, because the noise corrupts the digital signal. When we demodulate it, maybe we are receiving an error or bit error, whose probability of error could be defined by your Gaussian function. So we assume the noise to be normally distributed, right? Since that's a valid assumption actually, since we're talking about a large number of electrons, and if you add all that randomly distributed value of your random electron fluctuation, it adds up by central limit theorem. It adds up to become a normal distribution. So the Q function, right, let's define the Q function. Q of x is basically the probability when our normal distribution is greater than some value x of your Q function. Right? As x increases, your area under the curve right here, which is this, approaches 0. So it's a decreasing function. Right? So basically, it's the complement of your cumulative distribution function for your Gaussian distribution. Right? And just some properties, if you approach positive infinity, your Q function becomes 0. If you're at negative infinity, the Q function becomes 1. At exactly x is equal to 0, the Q function is 1/2. And if you add Q of x plus Q of negative x, you'll get always get 1. Okay. So just consider the following change of variable. Okay. Just the following change of variable. Let z be equal to x minus t. Then we're now just going to be integrating. Your dt will just become dz. Your x is just a parameter. It will be factored out from your integral. And you consider this exponent of negative 1/2 z squared. Using Taylor series, you get this expression inside. And you perform another change of variable. Let v is equal to negative xz. And consider the following integral. And this is called the gamma function. For a given integer n, the result of this function is equal to n factorial. Okay. For some x greater than 0, using the n plus 1 terms of the previous series you have here, okay, using the n plus 1 terms, we recast the q function right here. Okay, and all of these for x greater than 0, much greater than 0, I might add, this term right here becomes very small. So with this term, and so on and so forth, you'll be left with this value for your lower bound. So if you just approximate it, let this be very large, your x, your smaller lower bound of the q function becomes this equation right here, and the upper bound is when this becomes very small, right? Since x greater than 0, your q of x actually squeezes from the first term, which is 1. You have a 1 inside the parenthesis. And your first two terms, 1 minus 1 over x squared. So your q of x is always between these two values right here. For a very large x, second bound can be obtained by ignoring the x raised to minus 1 factor, and basically the maximum value of your q function is equal to this equation right here. Okay, so just the bottom line, basically your Q function behaves like an exponential function decaying at this rate, negative x squared over 2. So now let's define the measurement of efficiency. Your spectral efficiency is basically the amount of information rate in bits per second that can be transmitted over a finite bandwidth. Basically, your bit rate divided by the bandwidth. That's why the unit is bits per second per hertz. The energy efficiency is the number of bits transmitted per 1 joule of energy. Basically, your bit rate divided by the total power. Okay? So the reference is always the bit rate. We try to maximize always. We try with the given resources that we have, bandwidth, power, we always try to maximize the bit rate. So you increase the bit rate while maintaining your bandwidth and power, you're actually increasing both your spectral efficiency and energy efficiency. Okay. So that means our signal to noise ratio, when defined in terms of our digital communication system, your signal to noise ratio, which is still P over sigma n squared, where sigma n is the variance, sigma n squared is the variance of the noise, which corresponds to noise power. Well, it just becomes this P here is basically your bit rate multiplied to your symbol rate. Okay, so your bit rate multiplied to your symbol, sorry, not the bit rate, it's the energy per bit multiplied by your bit rate, rather. Okay, so energy per bit multiplied by your bit rate, that's the power. Your noise is basically the noise power and not multiplied by your bandwidth. So, sorry, the power spectral density of noise and not multiplied by your bandwidth B. So, in terms of our digital communication systems, our signal to noise ratio can be broken down with this in this equation, and the fair comparison between two modulation schemes is actually the SNR per bit, which is EB over N naught, the energy per bit divided by your noise spectral, the power spectral density of your noise. Okay, because this is used because the number of bits per symbol actually differ in your memoryless digital modulation schemes. So it's EB over N naught right here. So for binary PAM signals, an error occurs when you cross the decision rule, when your noise, which is distributed over this mean right here, if you transmitted this, your noise, your received signal will actually be distributed over this mean, and an error occurs if you cross over your decision boundary. If we assume equiprobable symbols, then your decision boundary right here will be at the middle of these two symbols right here. So the probability of error is basically the Q of your position, which is square root of EB, divided by the noise power, okay, or the noise variance right here. And you simplify this, you get this equation or this expression for your probability of error for your binary PAM signal. So in the case of 4PAM, in the first symbol, the error occurs when, again, your noise crosses over your boundary, right? And the boundary between these two symbols is at their middle. That means the boundary is at a distance, a square root of EB from both of them. Right? So this probability of error right here, given that 0, 0 is transmitted, is equal to this expression. If 0, 1 is transmitted, you have two boundaries that surround this symbol, 0, 1. Therefore, you expect your two components or two terms that will add together that will form the error, the probability of error rather, when you transmit using 0, 1. So in this case, you're using maximum likelihood. Alright. Okay. Same is true with transmitting 1, 1. And same is true, not same, since you're 1 0, when you transmit 1 0, it does not have an adjacent symbol in its right side, only the left side. You revert back to this expression right here. So the total probability of error, given this, assuming equiprobable symbols, is equal to 1 plus 2 plus 2 plus 1, which is 1 here, the coefficient here, plus 2 plus 2 plus 1, divided by 4. This is the probability, 1 over 4 is the probability that your symbol 0, 0 is sent, 0, 1 is sent, or 0 or 1, 1 is sent, or 1, 0 is sent, multiplied by your Q of square root of 2EB over N naught. Okay? Which is basically this equation right here. So just notice, okay, for your 4PAM, the minimum distance is actually, if you recall, the minimum distance is actually square root of 2 times your energy per bit. Okay, this is for your PAM signals, and your probability of bit error right here is actually equal to Q of the minimum distance, Q of the minimum distance, dmin, divided by the square root of N naught right here actually corresponds to the, what do you call this? The standard deviation of your noise. Right? So do well to note that. Alright, so let's look at the case for your QPSK, or for QAM, or for PSK. Basically, they're just equivalent. We can actually treat this as an independent analysis of 2PAM transmissions. Why? Because if you are displaced from this axis right here, if you cross over this axis, it doesn't matter if you cross over this axis or you cross over this axis, you'll always have an error. Right? It corresponds to decoding this as this if you cross over this axis right here. Same is true if you try to cross over this axis right here. And since the noise is independent, so the noise in this axis, the Q axis, is independent with the noise from the I axis, right? Because they're independent, identically distributed Gaussian noise. The probability of successful detection is equal to this. Let's say we transmitted 1, 0. So that is the probability that we have V1 greater than 0. So that is your first component. And V2 less than 0, that is your second component. So V1 corresponds to the first component, the I component of your symbol. V2 corresponds to the Q component of your symbol. Since they're again independent of each other, you'll just split the probabilities into these two. Okay? So this will just be equal to the probability of the noise crossing over the boundary in your Q axis right here. So since these two are equidistant from the Q axis, then the probability, the first term here is the probability that your signal crosses over the boundary, which is the Q axis. And this also represents the probability that your signal crosses over to your I axis. Okay? Oh, rather, I apologize for that. It's successful detection. So it's the probability that they don't cross over your I and Q axis respectively. Okay? So I hope that's clear. So this results into this equation right here, equal to 1 minus Q squared, where Q is equal to this. Okay? Then the probability of error is just the complement of the probability of successful detection. So the probability of error, if we just substitute that 1 minus this, we get this, which is basically 2q minus q squared, right here. In a very large signal to noise ratio, this q squared, remember that it's a decreasing function as your argument increases. This can just be ignored. At high SNR, you'll get this probability of error for your 4 QAM signal. So it's 2 times q of square root of 2EB over N naught. So basically, the probability of error as compared to your 2 PAM signal right here, your probability of error is actually double compared to your binary PAM. Right? So there you go. That's actually the price of transmitting I and Q at the same time. Okay, so that's the comparison that is being shown here. For QAM or for PSK has approximately twice the probability of error compared to your 2 PAM. Okay, what's the trade-off here? Your 4 QAM actually transmits 2 bits per symbol, while your 2 PAM transmits only 1 bit per symbol. That makes 4 QAM more spectrally efficient. So remember, the spectral efficiency is equal to the amount of bits per second per hertz, basically your bit rate divided by your bandwidth. If they occupy the same bandwidth, they have the same pulse, your 4 QAM is actually more spectrally efficient over your 2 PAM. In terms of energy efficiency, you can actually see that they have the same. They have the same energy efficiency, so you can verify that. Like comparing your 4 QAM versus 4 PAM, okay? So your 4 QAM is basically, again, approximately 2 times Q of this value right here. Your 4 PAM error, as we've shown earlier, is 3/2 or 1.5 times this. Right? Your 4 QAM is actually 2.5 times more energy efficient than 4 PAM. You can verify this by getting the average transmit energy of 4 QAM compared to your 4 PAM. Even though your 4 PAM is better, is more robust compared to your 4 QAM, it is actually more energy efficient since 4 PAM consumes a lot more energy compared to your 4 QAM. Right? So this is the calculation for that. So now let's look at a larger constellation. Let's look at your 16 QAM. The exact performance of such a large constellation is actually hard to compute. But an alternative solution is to use your pairwise error probability to find the bounds of performance. So if you are an engineer that is designing a communication system, you're not really interested in the exact performance of your system. You can use approximations to basically compute for the worst case scenario. And this is what you're doing, what this slide is doing. So we can find the bounds on the performance of our 16 QAM. So we know that the 16 QAM performs within that range. So if you want to really get the exact performance, well, you can try to just compute for the probability that this crossovers this, etc., etc. It's actually very difficult. Okay. Or you can just simulate it to compare it with others. Nothing's stopping you. But anyway, so suppose let's transmit your symbol x sub I. An error occurs if basically the distance of your received signal from x sub I is actually greater than the distance from some other symbol x sub L that is not I. Okay, so this is the minimum distance, Euclidean distance decision rule, which is derived from your maximum likelihood rule. Okay, the probability of symbol error can now be expressed. So the probability of error, given that we transmitted x is equal to xi, is basically the union of all the cases when your received signal is actually further from your transmitted symbol, okay, further from your transmitted symbol to another symbol in the constellation, okay, using the union bound approximation. So the union bound approximation goes like this: if you have the probability of a union of events, their maximum value is actually less than or equal to the sum of the probabilities of these individual events. So where did that come from? Well, basically, it just let's simplify this with a two events. So recall, if you have two events, they could be mutually exclusive. Right? In this case, in the Venn diagram, they're mutually exclusive if your oops, sorry. Let me just redraw that. They're mutually exclusive if their events do not have an intersection. Okay, say let's say this is the set of event A, this is the set of event B. The probability of A union A intersection B rather is 0, and the probability of A union B is basically the sum of their probabilities. Now, if you have mutually non-exclusive events, there you go, they actually have a union. So they actually have rather an intersection, a small intersection. So if you want to get the probability of A union B, so the probability of this happening is basically the probability of A plus probability of B minus the probability of A intersection B. Okay? Since they have some values that they intersect, right? Then it follows that the maximum value of the probability of A union B is when they don't have any intersection at all. And that value is when we add all the probabilities of your individual events from happening. Okay? So this will be the maximum value of your probability of error. Okay? So this can be rewritten right here. This can be rewritten like this. Okay? So it's the Q of the distance between your xi and xl divided by 2 times the square root of 2 and not divided by 2. So the distance, this is the distance of your xi from the decision boundary, right? And this is your noise power, right? And you simplify that, you get this expression for the probability of error, which is basically less than or equal to your minimum distance divided by the square root of 2n sub o. Okay? So, since we assume that the error are mutually exclusive, then the probability of error has a maximum value of this expression right here. So the probability of error has a maximum value. So this is the worst case scenario, okay, the worst case scenario for your system. And if someone asks you, okay, 16 QAM is what you're gonna use, what is its performance? So you show them that, okay, we cannot really exactly compute its performance, but we know that the worst case scenario is equal to this, right? So Murphy's law then, let's say this will occur. The worst case scenario will always occur, Murphy's law. So this is what you say, what you specify for your 16 QAM system. And your 16 QAM system would actually perform better since this is the maximum bit error rate. Okay? So just to compare, right, from here you can get the bounds, this m minus 1. So this is just the for your 1 given x is equal to x sub I. To get the total, you just divide that by m, M being the number of symbols. Since this is the probability, assuming equiprobable symbols, this is the probability of your symbols. Sorry, this is the probability of your symbols. The probability of your symbols being transmitted, and the bounds would be from here to here. Okay? At very high SNR, your bounds become tight actually, right? And your intelligent union bound, the union bound, and the exact value are actually becomes actually approximately equal. As you can see here, the intelligent bound is from here. At very low SNR, the prediction of intelligent union bound is actually higher, since actually your signals at low SNR could cross over the furthest reaches of your constellation. But at high SNR, your signals are mostly contained rather within its neighbors and its immediate vicinity. Okay? Again, at high SNR, if we transmit this, it can go anywhere in your constellation. Therefore, it has a lot of union. Okay? So it has a lot of intersection in all its events. But when you have a high SNR, so your errors are mostly contained within the vicinity of your symbol. Therefore, the union of or the again the intersection rather of your two events happening becomes almost zero. Okay, so that's for your QAM signal. Next is the PSK. So the information of your signal is in the face of your PSK. The distance between the 2 points, right here, two adjacent points, is basically this value right here. If we just plug in this value from this equation, will be the lower bound and this will be the upper bound. Okay. So basically, this is a universal thing in universal equation for two-dimensional signals. Okay. So now let's look at higher dimension signals. For example, FSK. So the kth symbol in terms of its vector is equal to this, where the kth element contains the energy. The received signal is basically your S plus your noise. Since the noise, again, the noise, just to refresh, it's independent and identically distributed Gaussian random variables. So your kth element would have the energy plus the noise. Okay? So the advantage of orthogonal signals, or FSK signals rather, is that the orthogonality can be exploited. Okay? So recall that our decision using your maximum likelihood rule, uh, it's very likely that our signal would be at the component with the highest power. So you just multiply this RT with all the S sub m and get the S sub m that maximizes this expression inside. So the problem is just reduced to the largest received signal component. So you just get the component with the largest signal. For example, if S sub 1 is transmitted, then the noise, or the received signal rather, would have the maximum value at the first component. Right? The probability of your correct decision occurs for assuming that S1 is transmitted. You get this correct decision if you get R1, and that is when R1 is greater than R2, R3, up to R sub m. So the minimum distance between FSK symbols is equal to this. So recall, by using this, the minimum distance, the probability is bounded by, again, you use that here, from your union bound. and you'll get this for your minimum and this for your maximum. And actually, just some note that if you increase m, your probability of error actually decreases. Opposite for what happens with QAM, ASK, and PSK. So this is the plot for your QAM. If you increase the number of symbols, your bit error rate actually increases. So you need more power just to maintain the same bit error rate level. For FSK, it's something like this. So as you increase, at this it's 65,536, which is unrealistic. But if you increase that, your FSK signal actually, well, it actually becomes better in terms of performance. And as you actually increase m, as it approaches infinity, it reaches this point around negative 1.6 dB. It will actually just be a step function at m approaches infinity here. Anything below that, your bit error would just fluctuate or would just be unpredictable. Anything beyond that, you'll get 0 bit error rate. So this will be relevant as we go along the course. And that's the end of this lecture. So just to summarize, uh, basically, your bit error rate is bounded from this value here to this value here. So basically, this is where the reliability of your system materializes. We used the minimum distance before as a metric for reliability. In this case, it actually has an effect inside your bit error rate. If you increase the minimum distance, you actually increase your bit error probability. And this is used widely in your two-dimensional signals, even in your three-dimensional, m-dimensional signals rather. Okay, so uh, that's the end of this lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Uh, Thank you for listening. I'll see you next meeting.